Hello, everyone. I'm Tom Keelan, here to give you a flash introduction to the Metalog distributions. The Metalogs were developed for a very practical purpose, to provide a family of distributions that is both more flexible and easier to use than the classical distributions with which you're likely familiar. You can see here on this chart, many thoughtful people have been saying very good things about the Metalog. Let's take a quick look as to why. Metalog distributions may be considered as an alternative to using the classical distributions. Wikipedia lists about 115 named continuous classical distributions. In contrast, in the Metalog family, there are about 60 practical Metalog distributions that comprise unbounded distributions, semi-bounded low, semi-bounded high, and bounded distributions. This expands the list of practical distributions that you may want to consider in your toolkit by more than 50%. Metalogs are likely your best starting point for fitting a continuous distribution to data. What kind of data? It could be expert elicited data where you've assessed from an expert 10, 50, 90 quantiles, and you want a smooth curve to go exactly through those quantiles. Metalogs are perfect for this kind of application, no matter how many data points you have assessed from the expert. Simulated data. If you have data from a simulation or from any such source, you're probably best off starting with a Metalog if you would like to have a continuous representation of that discrete data. Why? Because Metalogs can fit an arbitrary set of data more closely and more accurately than classical distributions in the vast majority of cases. The third category is empirical data. If you have empirical data from any source, it is you'd often want to use a Metalog rather than classical distributions to fit that empirical data, again, because it's more flexible and frankly easier to fit. So why do I say Metalogs are easier to use and more flexible? Well, Metalogs, first of all, have virtually unlimited shape flexibility. The equations in the Metalog family are like a Taylor series. They may have any number of terms. Practically speaking, Metalogs go from 2 to 16 terms, but you could have more than that if you wanted. The more terms you have, the more shape flexibility is there. Secondly, one can fit to data simply with least squares. This is important because it avoids the nonlinear optimization required to find the parameters of most or many classical distributions. Here, the fit to data is simply an ordinary least squares calculation. Third, there's a choice of boundedness with the Metalogs. You can have unbounded, semi-bounded, and bounded Metalogs according to whatever are the natural bounds for your application. This avoids the problem of having to cut off the tails or something else when you've got a distribution with a classical distribution with the incorrect boundedness associated with your application. 4, there are simple closed form equations. That is, the quantile function, the inverse CDF, is a very simple closed form mathematical equation, as is the probability density function, PDF. Fifth, the Metalogs are easy to simulate, given that you have a closed form quantile function. This means that the Metalogs, even though they were developed specifically for the field of decision analysis, the Metalogs, now that they have been developed, have virtually unlimited applicability in any field of human endeavor. Any field of human endeavor where you would use continuous probability distributions, you might just as well, you might prefer to use a Metalog. Let me give an example. Here is a set of empirical data shown on this CDF here of 3,474 steelhead trout that were caught and released in the Babine River over the years 2010 to 2014. The weights of these trout are shown on the graph. They range typically from 4 or 5 pounds up to a maximum of around 30 pounds. It would be quite typical to fit a set of data like this with a log normal distribution or some other distribution, semi-bounded distribution that has a similar shape. We're going to fit this data both with a log normal and with a metalog and look at the difference. A fact about steelhead trout, about their life cycle, is that the trout are born in the river, they go to the ocean, and when they come back to spawn for the first time, they're called one salt fish. Then they'll go back out to the ocean for a few more years, feed and gain some weight, come back up and spawn later as two salt fish. If you were to ask fish biologists questions like what are the relative fish weights and the relative population sizes between one and two salt fish, they would have no answer to this question. So let's explore this with metalogs. Here's the actual empirical data, the histogram, and you can see the best fit log normal distribution is the green curve. Now let's fit some metalogs. With a two-term metalog, you get something that looks like a lot like the log normal. 4, 6, 8, 10. Look at this. The metalog has detected a natural bimodality in the data. And could that bimodality be the one salt fish, the smaller fish, versus the two salt fish, second time spawners up? Very, very likely. This is an insight you wouldn't have been able to get from the classical distributions. Resources are available for metalogs if you'd like more information. There are free publications on the Metalog website, metalogs.org. There's a Wikipedia article on the metalogs. There's free Excel workbooks, so you can try them out on any data sets you like. Analytic Solver from Frontline allows you to fit both metalogs and classical distributions to the same set of data so you can do the comparisons. That's my summary for now. Hope you've enjoyed this flash presentation. Have a great day.